So good morning, everybody. Let me share my screen here. This somehow stopped working. Good morning, everybody. Welcome back to the CHEESE Advanced Training School on HPC for Computational Seismology. The plan for today is mainly two sessions, two code sessions. In the morning, we will look at the SeisSol code and do exercises with that. Then we will have a lunch break. And after the lunch break, we will start with a few lightning talks. And after that, we will do the code SpecFem 3D with exercises as well. And that's from my side. If there's no questions from the audience, then I would actually start right away. Is there any questions from you? No questions? Then I suppose Alice is going to present. Please go ahead.
Bo takes the lead. No,
okay. I'm here. Can you hear me?
Yes, we can hear you.
Okay, I will share my screen and start.
Bo, please turn on your video. We can't see you.
Oh, okay. Yeah, let me do it. Yeah, so you can see my screen?
Yes.
Yes.
Okay, I will start. Yeah, so good morning, everyone. Yeah, welcome to the SeisSol training. And the SeisSol is one of the flagship code in the CHEESE project, which stands for the Center of Excellence for Exascale in Solid Earth. So here are a list of the trainers today. And Anis, she already gave you some introduction about the SeisSol. If you want to find more information, you can go to our website or go to the GitHub, the repository. So today we will work together with you to do the SeisSol exercises. We cannot move to next slide. Okay. Yeah, so today we will cover three applications. The first one is the kinematic source model. We will use the 1994, the loss rage earthquake as an example. So you will start with a standard rupture format where you have all the ruptures pre-described. Then we will run our elastic model. So you will see how the elastic wave propagation and then see how the ground motions moves. Okay, the second one is a 3D deeping fault with dynamic rupture. This one we will use and implemented the plasticity. So you can also see that how the off-fault plastic deformations. We will use the SCAC benchmark TPV13 as an example. So for that, you can find more information about the benchmark in this link. The last one, we will use our complex dynamic rupture model of our earthquake that happened in 2018, the Palu Sulawesi earthquake. This earthquake is interesting because it's also generated the super shear rupture. Also, you have then a strong tsunami coupled. So before we move on, I first want to make sure, okay, we are going to set up the Docker so you can make sure you can use it during the trainings. So why we use Docker? Because, okay, in that case, we can pre-install some tools inside. So you can use it directly. You don't need to use it and install it anymore. So today we are going to use three tools in the Docker. One is Archive, where you can use it to generate then the kinematic source files. Then we will use the Gmesh and Pumpkin to generate the mesh files for you to our simulations. I think before we send an email asking you to install then the Docker, so hopefully you already done it. And so, yeah, if you already installed Docker, so now we need to set up the environment. So in that case, please open our terminal window, in your local computer. So for Windows, that is better to use than the PowerShell. So it doesn't matter whether you are using Linux or Mac or whether you are use Windows. Oh, sorry. You just run the same command, then it will pull out the Docker container to your local machine so you can access the tools.
Could we have a quick yes that everybody stop? Bo, can you pause? Can we have a quick yes that everybody has the Docker in the participant list? Could you click yes if it's all set up? You go back one slide, Bo, please.
I would also like to ask you to execute that command right now, because it takes some time to download, or might take a few minutes.
But that's the same we were asked to download on Monday or Tuesday or something, right? You didn't
Yes.
change anything.
Yes, that's the same.
Okay, good. So if I did it then it's fine.
Okay. Yeah,
So I don't see, no, oh, please go back. I don't see a lot of yes. I think we have to get more yeses here.
Oh, sorry, I didn't say yes or no.
In the participant list, you can see who's having a, we have 25 yes only.
Oh,
so
because
far.
now I'm in the screen sharing, so I'm trying to X.
29, 30, 31. 32. 33. If it doesn't work or you have problems, please hit no. So we know that you might need some advice later. 35. 36. And 0 no's. So I guess everybody's just still doing it. Let's wait one more minute. 38. Maybe we can quickly summarize again what's in this Docker. Carsten, would you like to?
Do you want to do it now? Because we have slides after, you know.
Ah, okay.
Yes, one no from Connor.
Oh, we have one no. Would you like to tell us what the problem is, Connor?
I might have missed the first 2 slides.
Yes, Bo, could you go back, please? And where you can get the Docker?
And Nico, you have to click yes also.
No, we don't have the link to download. Yeah. I think previously in the email that we provided the link to download this Docker installed.
Yeah, I did that.
Okay, so here
Okay.
you just need to open our terminals and run this command.
Just gives a permission denied.
I put the download link in the chat if someone needs.
Are you on Linux? Maybe you need to add a sudo to the command.
Yeah, that's it.
Okay, good. Yeah. So should I move
Perfect.
on?
Anybody else having trouble, or do you, I guess the other ones that didn't tick yes, then maybe still making coffee?
Yeah.
Then wait, well, you don't have to rush. Well, it's important that everybody has that running.
Yeah, I think because we will ask them again later. So yeah.
Okay, so we can go on for now. 43. Okay. If there's a problem, we will have 3 breakout sessions actually. So there's lots of opportunity to.
Oh,
fix
3?
things. Oh, 2. Let's see.
Okay, yeah. So today for today's training, we will also use breakout rooms. So at the beginning, before each example, we will have an introduction in the main room. We will tell you what's the required input files we need to run SeisSol, and we will go through then the input files to tell you what does the parameters we put there mean. Then we will go to the breakout rooms. Then you will also, prepare your meshes and prepare then the source files for the kinematic model. Then you will copy it back to the cluster, then submit the jobs. After the job is done, we will copy it back to the local machine. Then we will go back to the main room and we'll show you how to use the power view to look at the result and do some filters. So yeah, just in case if you didn't finish then the job in time, so here we also used our backup plan. So we put all the outputs there in the Google Drive folder, so you can download it. And we also put something in the cluster. You can go to this directory then to copy it. Yeah, so the first example, it will be our kinematic model. Then for the magnitude 6.7 Northridge earthquakes. This earthquake happened on a bland thrusting fault, which is not mapped before. So here is a map view showing then the historic earthquake and major faults in Southern California. The Northridge earthquake is here. And we also have a 3D view, so you can see that how the ruptures on the fault and the ground motions on the surface. You will see this result in your simulation later. Okay, so we will have also then second one is our dynamic simulation for the benchmark TPV13. The benchmark is then the SCAC and the USGS created. So you can, for people to verify different codes and softwares for dynamic rupture simulations. And today we are going to use this. Here is our map showing how the geometry looks like. You have a 16-degree deeping fault, and our rupture will nucleated in this 3 by 3 kilometer area. And the figure in the right is just shows that how the SeisSol code that matches with all other dynamic simulation codes. The third one is that the natural earthquake happened in 2018, magnitude 7.5 Pado earthquakes. And here, the figure here shows then the back projection result. You can see how the rupture propagating from the hypocenter, then the star marked, then to the south. This earthquake ruptured then left natural faulting, then ruptured several collecting the fault segments. And there's all really strong tsunami coupled, and so more than 4,000 people died in this earthquake. So we will run the simulation, and you will see how this super shear ruptures. So when you run after the simulation, you will copy all the results to your local machines, and we will show you what's the result I calculated. So there are time series. So we put the receivers on the fault or on the surface. So you can look at how that's ground shaking, the seismograms looks like. Then we also have the 2D output, that is the ruptures on the fault and the free surface ground motions. Then we also have then the 3D output, then how the wave field propagate in the 3D and the strain or the plastic strain. Then we will look at the result using panel view, and we also show you how to some simple filters to do the post-processing. So please make sure that everyone that the Docker works. Then I will hand over to Carson. Then he can explain more about the Docker. Carson, are you here?
Yeah. Okay, so I hope this worked out of you and you have Docker installed. Did you have to download the image in the meantime? Could I get a quick yes whether that was the case?
Yes, again, one no from Hasby.
Hi, can you hear me?
Yes.
So when I put the command docker pull blah blah blah, so I got an access the error response requested access to the resource is denied.
On which operating system?
Linux, Ubuntu.
Yeah, then please put a sudo in front of the of Docker.
Okay, yeah.
So this is something maybe I should explain. So for Docker to use, you need to be either part of the Docker group on Linux, or you need to add the sudo command. So that's yeah. So whenever we write Docker and you need the sudo, just put it in front of there.
No, I still get the same error.
Okay. Yeah, then we need to fix that later in the breakout rooms.
Okay.
Okay, otherwise I see a lot of yes. So please go to the next slide. Yeah, so for those of you for those advanced already, so this is a quick example how you can use it now. So basically, you can use Docker more or less as a command line tool. So with Docker run, you use with Docker run SeisSol training, you say, okay, I want to run the container that you have just downloaded. And now at the end, you can actually append a command with which you can execute a program. So this is something you can try out. So if you enter this command with gmesh -version, you should see 460, which is the version of gmesh that is installed. And if you see 460 printed, then everything should be fine. Yeah, so maybe give me a quick yes whether that works for you. Okay, 32 yeses, 33, so that looks very good. Then please go to the next slide. So yeah, you don't need to enter this command right away. I will introduce a shortcut in a minute. Just one thing, which is a very technical detail, which I don't want to go into much detail. But what we need to do is we need to kind of tell Docker where to find files that we are going to pass. So if we are later going to pass a file to gmesh, which it shall use to generate a mesh. And in order to let Docker find these files, we need this -v command, which maps the current directory in which you are in your terminal, which maps that to inside the Docker container. And the -u flag is there to fix the permissions on Linux, such that the files that created have the right permissions. So you don't need to copy that right now, because we are going to introduce a shortcut in just a minute. Yeah, so and if you are on Windows, then the command is a little bit different. So you instead of the brackets, the angular brackets, you have these curly brackets for PVD. And it is also going to ask you whether you want to share files, and you just need to click on share it. Okay, go on, please. So yeah, so this command is quite long. So what we did is we created a training repository. So please download this link. We also shared the slides within the chat, so you can also open the slides yourself and click on the link from the slides. And I would ask you to please download the zip the zip container and extract it. And in there you find a file called training.sh, and this training.sh is going to wrap that complicated Docker command that I've shown 2 slides ago. Yeah, so on Linux you can just say /training.sh and gmesh -version. On Windows, it's unfortunately not that comfortable. So on Windows, please use the longer command that I've put there below. Yeah, and just a quick hint. So whenever you have these long commands and then you need to type them all the time, which is very cumbersome. So there's a small trick which you might know already or might not know. So if you just enter Control-R into your history, so into your terminal, then what you're going to see is a small window where you can start typing. And if you then start typing Docker, for example, then it's going to search all of the last commands that you entered, and it's going to find the last command that started with Docker. So it's a very easy way to repeat previous commands. And if you hit Control-R a second time after searching, then you can actually cycle through the different commands that you entered. And yeah, the same thing also works in PowerShell on Windows. So please go on.
Excuse me, can you hear me?
Yes.
I tried to clone the Git repository, and giving the whole path is not working. So I give it until training, and it worked, but I don't find the directory archive or the main.zip after cloning.
So the link does not work.
If I copy the whole until main.zip, no. I have to clone the directory training. And inside training, I don't see the main zip.
Yeah, if you clone the repository, then that's the same. So it's just the link is just the repository in a zip, not more.
Okay.
So you can also just git clone the repository if you're more comfortable with that.
Okay, thanks.
Hi, I get this unknown comment when I try to run the training.sh.
I think you need to change to the, so you need to unzip the zip.
Yeah, no, I copied the content of the zip file into a folder. I went to the folder and tried to run it, and this is what I get.
Ah, okay. Yeah. So the reason why you get this is that you did not add any command that you run. So
okay.
So if you say training.sh, then yeah, then this should work. So unknown command means that so you can run gmesh, rconf, and pungent, and SeisSol. So those are like 4 commands that you have, and you need to choose one of them. Yeah.
Okay. Thanks.
I have a problem with the slide number 13 for the Windows, where we need to the Docker setup. Yes. So the PUVD should be the my home directory or the chosen one. Yes.
It's the current working directory. So you kind of you should see on the left side, you should see a path on your terminal window like C colon and then some path, and this is the current directory you're in, and this is going to be the same as pwd.
And for Windows, you should work in PowerShell to make sure that it works.
Okay, because I have an error, like the response from the daemon invalid.
Oh, you need to start Docker first. So on Windows, Docker is going to start a very small virtual machine, and you need to run that before you can execute that command. So you should have downloaded this Docker desktop, and if you go to your start menu, there should be like a Docker thing which you need to start first.
Yeah, I think it's already running.
Which terminal are you using? Are you using terminal or are you using PowerShell?
PowerShell.
Okay.
Yeah, okay. Maybe could you post the screenshot or something like that in Slack? I think we should continue because we also have some time. We have planned some time later on to fix some of these issues. So in the breakout rooms, we have a very long first session, and then we can work on that.
Okay.
And by the way, so if Docker does not work, we have provided a backup for everything. So it's then unfortunate that you cannot participate with that, but we also have a backup solution if we may move on to the cluster later on. Okay, then I think I hand over to Bo, right?
Yeah, okay, so I will stop sharing, and Thomas will start the example 1.
Okay, so can you see my screen and can you hear me?
Yes.
Okay, good. Yeah, so the first example that we will see is a kinetic rupture model that we will put into SeisSol, and then we will try to generate some ground motion. So a kinetic, what is a kinetic rupture model? So it's just so we will try to model an earthquake, but the earthquake would be predefined. That's we are not using dynamic rupture boundary as we will do in the next two example, but we model the earthquake finite source using a set of point source. Each of them would be described by a moment tensor and a source time function. So then it's a set of a lot of moment tensor with a source time function. That is, the source time function is our slip at the point evolve with time. So this kind of kinematic models are often derived from an inverse problem, like using seismic or geodetic data. And today, so we'll try to model the Northridge earthquake. So the model from Artzel et al. 1996. And so we use this model because it's a kind of an example on the SCAP web page of this standard rupture format that I will describe later on. So the fault is 20 by 25 kilometers. It's a planar fault and it's dipping 40 degrees. And so we kind of smoothed and kind of resample temporally and spatially the example source by adding much more point source and fine time steps. So you can see how this source looks like on the right. So you can see that, yeah, that's a final slip, and there's kind of a very heterogeneous slip. So, and this example will allow us to present the parameter file of SeisSol. And so we use this example because it's also more easy to parameterize than dynamic rupture source. There's much less parameters, and then we'll be able to first see these parameters. So the parameter files of SeisSol are composed of a main parameter file that we call usually parameters.par, which will define the input files and the output files, what kind of output we want to generate, at which spatial and temporal frequency. And this will also define some global simulation parameters, like, for instance, do we want enable local time stepping, or I don't know, other parameters. And then this parameter files also links to some other YAML file, which will specify the spatial variation of some of the input parameters. So these YAML files, they are read by the EASY library, which has been developed by Carsten. And yeah, basically it's EASY. It's composed of different components called maps and filter. A filter can specify a kind of a filter part of the domain, and then define on this part of the domain the parameters, and a map will just transform the coordinate to well, a map is kind of a function, let's say. And yeah, the main advantage of this EASY library is that we don't need anymore to have to specify the parameter setup inside the code. So then we don't have to, like, everybody who runs the SeisSol do not need to have their own branch. And so then everybody has the same executable, and the code just reads the parameters, and this favor reproducibility, and this is highly flexible. So this might look like a very formal description. So I just put an example here. So yeah, this is an example of this YAML file. And in this example, we define the density and the Lame parameters. And you can see that there's different components, like a group filter and a function map. And so the group filter, for instance, will say that in the volume region 6, 7, and 8, we want to define the rho, mu, and lambda. And so we can define them with a constant value, and this has a constant value. And outside these three groups, we define rho mu lambda as a function of the y coordinate. So using a function. So these functions, they don't need to be compiled. They are just kind of process on the fly by SeisSol. So that's a big advantage of EASY. Okay, so now we will have a look at the parameter file, the main parameter file. This parameters file is read by a Fortran routine, so it's based on the Fortran name list convention. So a name list is a kind of a block of parameters with different parameters in it. And you see that in these parameters, there's various name lists grouped by different concept. And for instance, there's a block equation which will define all the material properties, if we enable or not plasticity, for instance, or where do we, or the material, the file which define the volume parameters. Then there's a boundary name list, for instance, which enable or not a different boundary condition. But so in this example, we will have a source, a kinematic source that we define here. So we have to set up the file, the name of this file here. And then we have to set up also the mesh that we use. So we use SeisSol use HDF5 unstructured titular meshes. So we have to define the mesh here, the mesh name. And then there's a name list with different global parameterization of the run. For instance, the CFL number that we use, which so that's about the yeah, an algorithm. That's something about the algorithm, and then also quite interesting, there's this algorithm, this parameter, sorry, for local time stepping. So in SeisSol, each cell can have different time steps. So the large cell have a larger time step, but the time steps are grouped by clusters. So that means that the smallest cell have time step dt, then also have available 2dt, 4dt, 8dt, so all of the power of 2. So, and if we use that, we have to use a cluster LTS equal 2. And then we have to define the outputs. So, for instance, all the output will be written in this folder output with this prefix, Northridge. Here in this block, you can see the parameterization of the volume output, and so at which interval do we output the volume, and which refinements we use. So I will explain that later. But for this setup, we disable volume output because this generates some large file, and so we have a limited space on the cluster. So we only output the wave field at the surface. So with this surface output parameters. So we enable the surface output at a time interval of 1 second. And then we use, so this refinement parameters means that if it's equal to 0, we will output 1 triangle by a mesh cell. But with SeisSol, we have we have subcell information. So then we can also generate more output for one cell. So if you put surface output refinement equal 1, then each mesh cell will be subdivided into 4 cells like that. And if you put 2, then each subcell will be also subdivided into 4 cells. So then there's even more spatial discretization. then we have some parameters to define the ASCII receiver. So if we want to generate some seismograms, so we will we link to this ASCII file. So we have six points with a sampling rate of 5 milliseconds, and we in this nameless abort criteria we define the final time of the simulation. So the SeisSol will run for 10 seconds and then stop. Okay, and the off-fault receiver file is just an ASCII file with the coordinate of each receiver in it. So nothing complicated. Usually in SeisSol we use a convention of Z positive. So actually this is only important for a dynamic rupture because you need to have some referential to define the strike and the dip coordinates in the fault output. So the source is described in the standard rupture format. So this is a format which has been proposed by SCAC, so the Source California Earthquake Center. And in this ASCII file format, we store the momentum source. So it's restricted to double couple and also the source time function. So here there's a link to the specification file, but basically this file is made of blocks. So each block would describe one point source, and in this block you will get the coordinates of this point source, the faulting mechanism, the area of the point source, the initiation time of the point source, time step, and the slip rate time history. Okay, so now what we will do is we will split into a breakout room. So we'll try to process this source file into a file that can be read by SeisSol, and then we will try to connect to the cluster, run SeisSol, and then analyze the output.
Okay, before we do that, I see there's some questions still going on in the chat about Docker, but are there any questions about running a simulation using a kinematic source? Any of these things that were just covered? Because this is what we will do now. Okay, then I suggest we split up. So we will have 6 breakout rooms. And the goal is to spend 45 minutes getting everything up and running, submitting your kinematic earthquake model. And you will also look at some output together and hopefully fix Docker problems. Should we? I don't know if should people with Docker problems maybe stay a little bit in the main room with Carsten? What do you think? Because otherwise, we might have Docker problems in each breakout room.
I think that's a good idea. So the people that have Docker problems, they just don't click on the button to enter the breakout room. They just stay in the main session.
Yeah.
Okay, I create the rooms.
An empty room, no? There would be a room without the instructors, and it is.
Yeah, we just make 5. We just make 5 tomorrow. I think.
Okay.
Okay, 5 breakout rooms. I would assign people automatically, and the instructors, please distribute yourself across the rooms.
Okay, perfect.
Because you will be assigned as well.
Yeah, and those that have the Docker problem stay in the.
Yeah. So everybody pressing the button to join the room, with the exception of the people with Docker problems. And instructors can then move from one room to the other.
Okay.
If necessary. There's still many participants here in the main room. Are they all having problems with the Docker? Or...
Jose?
Yes?
Okay.
No,
Just,
no, Taufik, you can go.
Okay. Jose, I was in the same room, breakout room with Duo, so please assign me to another room.
You are co-host, so if you go to breakout room and you put your mouse at
okay.
Open the breakout room menu, and then there's room. Next to it is a number with the participants, and put the mouse above that, and you can say join this room.
You mean the breakout room?
Yes, but I can do this also manually. So in which room do you want to go?
I was in the room number 5. So other than room number 5. I don't.
I think you have to go back into the room, otherwise you cannot assign you to another one.
Okay, I joined back to room 5.
Yes, please.
So you can also ask directly questions. So to Sonia, so could you please post the exact command that you used?
Carsten?
Yes.
So the setup from page 11 on the slides, that worked with the version. So that worked fine. When I tried to run now the command which I posted in the chat, it didn't work.
So that's on Windows and PowerShell,
Windows
right?
PowerShell, exactly.
Yeah, could you maybe also try the alternative so that you directly give the path? So with this,
what you suggested to Daniela?
To Daniela, yeah.
Okay, I'll try that.
Carsten, I have the impression there's one instructor less. Is there another instructor here in the main room at the moment, or are you the only one?
There's Taufik now trying to get, but otherwise I'm the only one.
Okay, Taufik, what happened?
It was already Thomas there.
So then I put you in room number 1.
Okay.
Okay, so you have to go back again, and then I put you in room number 1, sorry.
Sure.
Carsten, if I try to run it like this, I get a lot of output for Gmesh related.
Oh yeah, then it's fine.
Then it's fine.
Yeah, yeah.
Okay.
So this is so if you see a lot of output, so Gmesh, how to use it, blah blah blah, then this is fine.
Okay,
okay.
perfect. And then just to let you know, it worked with the alternative command for me as well. So I will leave now to the breakout session.
Okay, great. So Sonia, there's a space missing between the shared and UPOV-C. So I write it in the chat. So you need to, there's just a space missing.
Okay, okay, I'll try it.
Jose?
So the alternative command, so David asked that, so if this $PWD stuff does not work, you can also try to directly set the path. So I posted another example again. So this is an example I created for Daniela, but you could also just put your own path there. So slash.
Now it gives me a lot of it says that Gmesh and then lots of alternatives.
Yeah, then it's fine.
It's fine. Okay.
Yeah.
Can I interrupt a second, Taufik?
Yeah. 1, 2, and 5 is already has instructor.
You can also switch the breakout rooms by yourself. So you should be able to, and then just click on join breakout room, and you should be able to find
I think I will put you in room number 3 because Aniko, I think she said she wanted to have a second one there.
This number 6?
Okay. 3. So.
Okay, I will just.
David, you're also missing a space. So you put, you have /shared and then you have /opofc, and you should actually put a space between / and opofc. So that's the issue. So you have kind of written, I write it in the chat. So that's what you have written, and you should actually have a space there. So David, could you try the command I've put into chat? Yes, David, now it's fine.
Okay, thank you.
Yeah, you're welcome.
That file, we should put it in the working directory, the unzipped one. On the next slide, that's the 14.
Yeah, just put it in the working directory. Okay. So hi, Silikbet. So how do you pronounce that? Your name?
It's just better.
Ah, okay, better. So there's we had this error before, so most of you missed kind of a space between shared and OPC. So that was usually the error that others had. So I write it into chat, so you have something like this, and actually there should be a space here. And everything.
I think I used that. So I'm checking again. Yeah, I used that one space, right?
So maybe could you just put share the complete command that you use?
Yeah, sure.
Yeah, there's actually the space missing. So which I put in the chat.
Between the shared.
Yeah, between shared and OPC. So between there should be a space.
Okay, now yeah.
And I think you also have to add the drive name in front. So I think what you need is just type it. Yeah, so I think this should be the command.
For that file, so we need to unzip it, and then we need to go inside the file and run the command on the page number 14.
Yeah, let me just open the slides so that I know which slide you're referring to. Okay. So you are on Windows, right? So you don't, so there you can't use this training.sh script, unfortunately. So you should just use you just use the long command with docker run blah blah blah, and then comes gmesh, and you can just replace gmesh then by the other commands that come during the training. So I think for now you can move on to the next steps.
Hi again. So I tried your command, but the problem is that if I use this, it says the pathway for my working directory is not shared from the host, and it's not known to Docker. So maybe I couldn't use the name of the current directory. Just I should direct the shared one.
Did you get a get a small pop-up on Windows which asks you whether you want to share the directory?
No. But for example, if I'm just copying that. Yes. So this was an error if I used what you wrote in the chat.
Okay.
But if I use this one, and it just shows you information about the geometry mesh and etc.
You are on Mac. Okay, I thought you were on Windows. Sorry. Yeah, then you don't. So the C is wrong. The C is for Windows. I thought you were on Windows.
Oh, okay. So,
Yeah.
okay, no,
So
I use
if
Mac.
if your command works, then that's fine. Then just go ahead.
Okay.
But I actually think you need backslashes, so not the. And I think you should also be able to use this command here. So actually, on Mac you should be able to use this training.sh file, which I provided in the zip that you had to download. So you can use that on Mac. So I would recommend that if you are on Mac.
Okay. So this is the next step, right? Training.sh.
Yeah, you can use that on Mac.
Okay.
Okay, is there anything else someone needs? Otherwise, I would just join a breakout room and help out there.
Okay, how do I join the breakout room now?
Okay. Do you see that button, join breakout room?
Yeah, should I click just?
Yeah, just click it.
Okay, thank you.
You're welcome.
Hello. Welcome back.
Hello.
Hello, Amin.
Everybody is back.
Okay, super. So it's Taufik's turn now to give us a ParaView tour, and I hope everybody had some jobs running. I think from chatting to the other trainers, our group was the slowest. Sorry, but maybe you've seen what the output that was produced, so some of you already looked at it. So it's a very practical kind of output because it's only the lightweight slice of the wavefield output only at the free surface. And now Taufik is taking over,
Alice, you're muted.
explaining how to. No, I'm not muted.
Oh, I can hear you. Yeah.
So we can hear you, yes.
I can hear you.
Yeah, okay, super. Good. I anyway just talk to introduce Taufik, and he will now, after copying the files, and you've seen there's two kind of files, a short version that you just computed hopefully, and a long version for 10 seconds. And yeah, you use ParaView like yesterday to make a very simple shake map. Taufik.
Yeah, thank you. guys. I will share screen. Okay, this is what we did. Okay, it's not done. Okay, make sure you can open your ParaView that you already installed. Here we use the ParaView 5.8.1, that latest one. To open your output folder, output file, you can click this icon, open, or use the file, then open. Then this window will pop up, and make sure you choose the XDMF file, the file with XDMF extension. If you open the others, it won't work. So here, like Alice mentioned before, the one that we output here is there are 6 test receiver. It means that this receiver points that located in the surface. Today we will focus on the surface output. So here we only output the surface, but because we only activate the surface output. Later in the parameter file, parameter.var, you can always check. You can always change the output, like adding also the wave field output and fault output. Select the test surface and click OK here. And make sure you choose the XDMF reader. If you choose the other, in some cases it will crash, and you have to open again your ParaView. Then if you done so, you can click and then click OK. Then don't forget to press apply here. Then this will come up. Here you see the like in previous slide, you see here the eye is not open. Here the eye is open. It means that it's the one that shown here is the test surface, the XDMF. If you have another file, you can always check with this eye it's open or not. Then you can select the attribute here. You see the partitions, and you can see here, if you click, you will see big U, V, and W. It's means it's displacement, and a small u, V, and W. It means velocity. Here we can try with W. It means that U, V, W. It means that velocity in XYZ direction. Later, if you don't W, later it will you have to move the time to the last time step, because if there's nothing recorded shown in the initial time step 0, then if you don't so, it's sometimes it is shown like this. It means that if you see the scale bar, it's shown 0, 0, 0, 0. It means that your data scale is too small. You need to rescale the data range. You can do this by clicking this. It's automatically rescaled to data range. Or you can also rescale to custom data range. Like for example, here, if you click this with the C, the custom, then you can put like minus 0.3 to 0.3 and click rescale. Then it's shown different. So, but you can see here the scale bar now have a minus 0.3 to 0.3, which is nice. Then it's also useful doing visualizations, sometimes you want to see, okay, you want to see your elements age, then you can select surface with age, then it's shown like this. You will see that we have finer elements in vicinity of our fold. Then later it will explain in the next example, but here this is the advantage of using SeisSol, that we can do coarsening here. Then what we want to do is to try to use a calculator. By clicking this calculator icon, we want to compute the velocity geometrical mean of the velocity by okay, you click the calculator, and then don't forget to put the name of your variable. For example, here I use the geo mean, and then square root of u multiplied by v. It means that we only took the horizontal velocity. Then if you click apply, then it will automatically compute and generate the new attribute named geomean. Next, we want to apply a filter. Here, I suggest you to use a temporal statistic by clicking the filter and then alphabetical and temporal statistic. You could also use the search button command here, search, and then type. If you already know that your name, your filter name, you can also do search and type temporal statistic, and it will come up. Then, if you click that, then you will have this windows. Then you can click yes. This temporal statistic means the filter will process all time steps, which is and it takes sometimes to process. And click yes, and then we select we interested in the maximum value. Then we select the compute maximum. You can also do minimum and average for later purpose, but in this purpose we use the compute maximum and then apply. Then it will generate a simple check map. It's basically taking the maximum value of the geometrical mean for all time step, and it's basically a simple peak ground velocity, which is quite useful for dynamic rupture. I think this is all the last slide of the parview for the exercise 1. Of course, we can do much visualization, but you can play around later. Okay, now I think I can pass it to Duo.
No. Wait, Taufik. No, first you want to see if everybody looked at it.
Okay.
See if there's questions.
Is everyone having trouble with parview?
So on that last step, when I run the temporal statistics on both the short and the long outputs,
yes,
all it does is bring up kind of a beigey gray thing. It doesn't actually show.
You mean this one?
Like the last slide, yeah. Well, I don't know. Once you apply the compute maximum, yeah.
I think I have the same problem.
I think you have to change it from solid to geomean maximum. I mean the coloring in the properties tab.
Yeah, can you check in the attributes here?
Yeah, the geomean maximum, yeah, thanks.
Yes, yeah. It's a very simple, it's just a very simple filter. You can always have, there are a lot of filter available in the parview. You can always combine and create something else. we will have another preview exercise later in the exercise 2, which also combined like the fault output and then the 3D output. So we can play around much better later.
I just want to make sure that everybody caught what Taufik explained about the filter. This is something useful in PowerView, just for quick post-processing.
Yeah.
It was a bit fast, I think.
This one?
Mm-hmm.
I can come back. Okay. So yeah, here we choose the temporal statistic. So the temporal statistics works like because we apply this filter to the computed geomean. So this geomean compute for every time step. It's for this specific step. But then we with the temporal statistic, we take the maximum value of from all computed geomean. So that's why we choose the compute maximum from all the available time step. For example, from 0 until 10, we have 10 time step here. We took the maximum value of the geomean from all time step.
Okay, so at this point, I would like to have from other participants that are ready to go to the dynamic rupture examples a quick yes. And if you have any other question about kinematic source examples, then please put a no, so we can know where we stand. Because now we would continue with more with the dynamic rupture modeling, so really solving for spontaneous earthquake rupture coupled to seismic wave propagation. The next 2 examples. So let's see. We have 16 yes, 1 no so far. 17 yes, 19 yes. Okay. The no is from yes, yes, yes. Okay. 31 yes, 33. Okay. All right. So then we will continue with the next topic, and that is how to produce a dynamic rupture earthquake simulation. And we have 2 examples, a simple and more complex one, and Duo is the one that is taking over at this point.
So do we need a break before, or we start from now?
No, I think we should continue, and then maybe we will have a break during the breakout session. Like people that are finished or that need a break, they can just do that in the breakout session.
Okay, then I will start to share my screen.
Okay, I will stop share first. Yeah.
Okay, can you all see my slides?
Yes.
Okay, thanks. So in the second part will be dynamic rupture modeling. So in the first example, I will show you the dynamic rupture from SCAC benchmark center. The model have a single planar fault surface and a relatively simple setup. So it's really suitable for beginners to start off. Here is okay. So I will summarize the SCAC benchmark. So we have a 60-degree deeping normal fault, and it's 30 kilometer long and 15 kilometer wide. So the nucleation is in the center down deep on the fault. This example, this benchmark is a homogeneous half space, and it considers all fault plasticity when the elastic limit is reached. We use linear slip weakening to control the dynamics on the fault, and the initial stress condition is depth dependent. the nucleation is achieved by a pre-described nucleation patch, and the initial condition have strong super share in the results. So first, we will build a mesh for this dynamic simulation with the free software called the GMesh. So this is the input file for the GMesh called .geo. I will explain this geo file step by step to help you easy to understand the structure of the geo file. So first we define some important geometry in the fault. For example, the fault length, the fault width, and the dipping angle. And we also define the mesh discretization here. And we need to build a volume around the fault. Normally, it's 3 or 4 times larger than the fault dimension. Okay, so the structure of GMesh is like you need to build from points to lines to surface and to volume. So here, let's begin to create points. So the command in the GMesh language is really simple. So you should be able to understand it very easily. So first, I create 4 points on the surface and connect 2 neighbor points. I will make some line. These lines can make a clockwise loop, and then I will make a surface from this loop. So with a similar method, we can create the fault surface, which is shown here. And we can also create the nucleation patch around the fault. So the loop around the nucleation and the loop around the fault will give you the fault surface together. We need to define the identification for each surface that has been created in this geo file. For example, we use an arbitrary number file for each surface. So yeah.
Sorry.
Now,
excuse me.
Yes.
One question. So when you define your points, you have 4 parameters there. So the first 3 are x, y, z coordinates, and then you have some sort of, for example, here for this point 200 is LC underscore NUCL. Is that some sort of label, or what's the function?
It's a good question. Yeah, that is a fault discretization here.
Okay.
So example,
Yes.
I assign the maximum mesh in the domain, which is 22 kilometer, and on the fault, I want to refine the mesh, so it's 750 meter. So yeah, it's a good question. So the 4 column in the points will be x, y, z, and the resolution or the mesh size that you want. Okay, yeah, is there? So when you have the surface ready, so the next step is define the boundary condition that will be used in SeisSol. So SeisSol identifies 3 types of boundary conditions: the free surface, the fault boundary, which will have the dynamic rupture, and the absorbing boundaries. So the 101, 103, and 105 is fixed for SeisSol. So now, yeah, you have so now this is the basic structure for the geo file. Is there any other questions for the mesh file?
Excuse me, I have one question. The absorbing boundary is for the fault, not for the domain, no?
The absorbing boundary is for the domain.
Okay.
Yeah. So the fault boundary will be a fault surface, and the free surface is on the top of the domain, and the other 5 surfaces around the domain will be observing boundaries. Yeah, it's a good question. Is there any other questions? If no, then I'll move on to the next parameter. Oh, sorry. Yeah, I forgot the last part will be like design the mesh size. So this is a little bit difficult than the uniform mesh size we use. So we can assign a coordinate away from the fault. Use the module called the field in Gmesh. So first we can design a field called distance. It means like it will return the distance to a surface that you want to refine. This will be our fault surface. And the next module is called the mass eval. You can assign, for example, here I design second order polynomial function, which is based on the distance to the fault surface. So it will coordinate the mesh size from away from the fault surface. For the detail of this this mesh coordinating, you can read more details in Gmesh tutorial or visit our SeisSol documentation. Yeah, that's it. So the next part will be the parameters for this example. As in the last section, Thomas has already showed a lot of stuff in the parameters. So here I will just highlight the difference in this example. As we use fault plasticity, so we add 2 extra variables at the beginning of the parameter file to tell SeisSol that now we start to use plasticity. And there is another parameter, viscoplastic relaxation time, you need to give. And as now we use dynamic fault boundary conditions, so we need to turn on the boundary condition here. So yeah, so we use in the material parameter, the YAML file is the same as Thomas introduced in the first section. So here we use the easy map to assign the elastic and the plastic parameter. And as I showed, this benchmark uses a depth-dependent initial stress condition. So here is how is 3 principal stress, sigma 1, sigma 2, sigma 3 will change with depth. So this is a function. And you can see use this several lines in this YAML file. We can easily assign the initial stress for the example. So for example, the maximum compression stress sigma 1 is a depth dependence, so which will like here have the format here. So for the detail of this YAML file, you can read our Google Doc here as the link shows. And another difference is that we use friction law in this dynamic rupture. So now we choose linear slip weakening friction, which is FL2. And we also need to assign the parameters related to the friction in another YAML file called the fault.yaml. Okay, the nucleation is related with static friction coefficient. So in this benchmark, we in the nucleation we assign a smaller static friction, and outside is a normal static friction coefficient. So it will spontaneously nucleate in the nucleation zone for this example. So, okay, and we are interested in the physics on the fault. For example, the traction, the velocity, the rupture velocity, the slip rate. So here, with this output mask, we can customize which variables we want to output and which variables we don't need. So this 1 means we output, 0 means we don't output. And for the position of each number, it represents the different variables here. So I will not go into detail, but you can read it from our documentation. Okay, and then the mesh file in the exercise later we will create the mesh together, and the local time stepping is the same as in the first example. Okay, and which change the name for the output, and in this exercise we run for just 4 seconds to save time. Yeah, that's all for my introduction. Is there any question for the mesh or the input parameter? If there is no question, then we will go back to breakout room to do the exercise as in groups. My colleagues and I will help you to do the exercise. And we will do the power review to visualize the results in the breakout room as well for this exercise.
Do you want to keep the same breakout rooms as earlier, or do you want to change the number?
Oh, can be the same.
Okay.
So there's a couple of detailed slides, how just different power view tips and tricks, or what you can use to visualize the results. There's something about choosing the color scale, how to add a time annotation, and how to do a clip so you can actually see the fault. And I suggest you trying that maybe over the lunch break, if you run, because we really want to get to the Palu earthquake in our last 30 minutes, and then ask anywhere, Slack or email or chat or whatever, if there's problems with that. But it's more like a ParaView introduction, how to like make nice visualization, have a time annotation when you do a video and these kind of things. More importantly, were there any problems in running the job? Was everybody able to submit TPV 13? That's yes. More important than.
Hello.
Mm-hmm. Hello.
Yes. I see.
Yeah, I think some have submit, but they're waiting. I don't know if the cluster will work like normally to finish it, because normally it should take just 7 minutes.
Okay. Yeah, but let's go back and then we planned another little breakout, and then we can check if the job's finished or not in the next breakout room for everybody. But it would be important, I think, to have your own setup run. Okay, so the last example, and we're scheduled to finish at 12. So we have again a little introduction that Aniko will do, and then we have a last breakout, and we should meet here back in the main room 10 minutes to 12 to wrap up.
Okay, so the third example will be the Palu Sulawesi earthquake. Probably you have heard about it. So 2018, there happened an earthquake in Indonesia on the Sulawesi island that you can see here. So this island, as you can see, there's a very complex tectonic setting. So this earthquake was due to tectonic loading. Here we have a closer zoom to the fault system. We have a strike-slip fault system with very shallow depth where the earthquake occurred. And this earthquake was followed by a huge tsunami, which was very unexpected because normally in strike-slip fault systems, we would not expect a tsunami, maybe only for subduction zones. So here you can see again this fault system, and the main event, the upper event, the 7.5 event, was followed later on by two smaller events, by here a 5.3 and a 6.3 event. And those events provide us constraints on the dip angles of the individual fault segments that you can see here at the right-hand side. So from this information, from those earthquakes, we can then create a complex 3D fault system, as you can see it here at the right-hand side, with different dip angles. So a northern segment with a dip of 65 degrees, Palu segment with a dip of 65 degrees as well, and then here as a loopy segment with a dip of 90 degrees. Again, we will have a parameter setup. So we will have our parameter file and several dependent YAML files. In this case, we will have a fault YAML file, which constrains the fault geometry, an initial stress YAML file, which contains the initial stresses in 3D. Then we have a material 3D YAML file, which has all the initial stresses and Lamé parameters in there that we will need for our dynamic rupture simulation. And then we have the nucleation stress YAML file, which describes a forced nucleation within a predefined patch. So we will go through the parameter file again, but very fast due to the lack of time, and also not that much changed from the last parameter file. So of course here we changed the name for the material file. So we have Sulawesi material 3D YAML file. The plasticity is turned on, so we have off-fault plasticity. Then our friction law is 100, which means that we have a rate in state friction law. This means that we have a nonlinear relation between the fault stress and the slip. Then our model file name is Sulawesi fault YAML. And here we define some rate and state parameters where we will not go into detail right now. Then here we have the moment rate output turned on. So afterwards we can look at the moment rate of the earthquake, and the output type is an ASCII file. We can see here that our time interval output will be 0.4, and we will place some fault receivers on the fault. Then our mesh file. In this case, we will not create the mesh. The mesh is already created with PAML, and it is inside the folder where you will run it. And it is the Sulawesi 65 dip straight A, short north micro mesh file. We use local time stepping again. And the output will be written to output Sulawesi. Then what is interesting is that we will place off-fault receivers. So we will not only have receivers on the fault, but we will also place them spread it around the fault. And we have 33 receivers. And the receivers, the record points, so the points where the receivers stand, are in this DOT file, GPS filtered projection DOT. So the sampling of each receiver is 0.01. So this will be the sampling of the seismograms afterwards. And here you can see the 3D material properties. So this here would be the S-wave velocity that we use as an input for our model domain. So you can see here the model domain and our fault system within this velocity range. And you can see that we have varying velocity from east to west and north to south and depth. So that's it, hands-on again, I would say. And I don't know, Alice, will we go to breakout rooms again? Yes, so we will go again to breakout rooms. And within the breakout rooms, we will run our example and then look at the output.